the last chapter, we developed the concepts of position, displacement, velocity, and acceleration that are needed to describe the motion of an object along a straight line. We found that the directional aspect of these quantities can be taken care of by the positive and negative signs, as in one dimension only, two directions are possible.
Now, we will deal with kinematics of a particle moving in two dimensions. Knowing the basics of two-dimensional motion will allow us to examine, in future chapters, a wide variety of motions, ranging from the motion of satellites in orbit to the motion of electrons in a uniform electric field. We begin by studying in greater detail the vector nature of displacement, velocity, and acceleration.
As in the case of one-dimensional motion, we derive the kinematic equations for two-dimensional motion from the fundamental definitions of these three quantities. We then treat projectile motion and uniform circular motion as special cases of motion in two dimensions.
We also discussed the concept of relative motion, which shows why observers in different frames of reference may measure different displacements, velocities, and accelerations for a given particle. Motion not confined to a plane, such as a car following a winding mountain road, is described by three-dimensional kinematics, and thus, the real world is three-dimensional.
Projectile motion is the motion of an object thrown or projected into the air, subject to the only acceleration of gravity. The object is called a projectile, and its path is called its trajectory. The motion of falling objects is a simple one-dimensional type of projectile motion in which there is no horizontal movement. In this discussion, we consider two-dimensional projectile motion, such as that of a football or other object for which air resistance is negligible.
For a projectile fired from a ground at an angle theta above the horizontal, the projectile rises to some maximum height and then descends. It finally lands at some horizontal displacement from its launching point. The horizontal displacement is called range. The magnitude of the range, usually represented by the uppercase letter R, is the horizontal distance traveled by the projectile between the launching position and the landing position, on the assumption that it returns to the same level at which it is fired. The launching speed and the angle at which projectile is launched affects the projectile's trajectory. The horizontal component of the projectile's velocity is constant, and acceleration is 0 meters per second squared, while the vertical component of velocity is changing and acceleration is due to gravity.
The range is independent on the angle of projection. It can be shown that maximum range occurs when the angle of projection is 45 degrees. It can also be shown that same ranges are obtained for two identical projectiles fired at equal initial speeds if their angles of projection are complementary. For example, projectiles launched at angles of projection of 30 degrees and 60 degrees for a given initial velocity cover the same range.
For our first example, a rifle is aimed horizontally at a target 30 meters away. The bullet hits the target 1 9/10 centimeter below the aiming point. What is the bullet's time of flight? What is the muzzle velocity? First, we define our coordinates. We will use the coordinate system indicated in the figure, where the origin is placed at the tip of the gun. Then we have x sub 0 is equal to 0 and y sub 0 is equal to 0. We also know the acceleration, a sub x is equal to 0, and a sub y is equal to negative 9 8/10 meters per second squared, or the acceleration due to gravity. The gun is fired horizontally so that the initial velocity in y is 0, but we do not know the initial velocity in x. We do not know the time of flight, but we do know that when x has the value 30 meters, then y has the value of negative 1 9/10 times 10 to the negative 2 meters, or 1 9/10 centimeter. Our equation for the y coordinate is the fourth kinematic equation in y terms. We now have y, which is equal to y initial in y times t plus 1/2 a sub y t squared. Then we have y is equal to 0 plus 1/2 times negative g times t squared, or simply y is equal to negative 1/2 gt squared. We can now ask, at what time t does y equal to negative 1 9/10 times 10 to the negative 2 meters? Substitute y, which is equal to negative 1 and 9/10 times 10 to the negative 2 meters, and solved y, which is equal to negative 1 half gt squared. T squared is now equal to negative 2y over g, which is equal to negative 2 times negative 1 and 9/10 times 10 to the negative 2 meters, all over 9 and 8/10 meter per second squared. T squared is now equal to 3 and 8800 times 10 to the negative 2 second squared. Getting square root of both sides, we obtain T, which is equal to 6 and 2300 times 10 to the negative 2 seconds. To solve for question B, the equation for x motion is x, which is equal to v sub 0 in x times t plus 1 half a sub x t squared. We now have x, which is equal to v sub 0 in x times t plus 1 half times 0 t squared, which is simply x is equal to v sub 0 in x times t. For part A, we know that when t is equal to 6 and 2300 times 10 to the negative 2 seconds, then x is equal to 30 meters. This allows us to solve for v sub 0 in x. V sub 0 in x is equal to x over t, which is equal to 30 meters over 6 and 2300 times 10 to the negative 2 seconds. And v sub 0 in x is equal to 481 and 5400 meter per second. For our next example, you throw a ball with a speed of 25 meters per second at an angle of 40 degrees above the horizontal directly toward a wall as shown in the figure. The wall is 22 meters from the release point of the ball. How long does the ball take to reach the wall? How far above the release point does the ball hit the wall? What are the horizontal and vertical components of its velocity as it hits the wall? To solve for A, we will use a coordinate system which has its origin at the point of firing, which we take to be at ground level. It is when the x-coordinate of the ball is equal to 22 meters. Then let us write out the x equation of motion for the ball. The ball's initial x velocity is v sub 0 in x, which is equal to v sub 0 cos theta sub 0. When substituted, we have 25 meters per second cos 40 degrees, which is equal to 19 and 2/10 meters per second. And of course, a sub x is equal to 0, so that the x motion is given by x, which is equal to v sub 0 in x times t plus 1 half a sub x t squared, which is now 19 and 2/10 meters per second times t plus 1 half 0 times t squared. We solve for the time at which x is equal to 22 meters. From the previous equation, we will now substitute the given and the obtained values. We have 22 meters is equal to 19 and 2/10 meters per second times t. And t is now equal to 22 meters over 19 and 2/10 meter per second. T is now equal to 1 and 1500 second. The ball hits the wall 1 and 1500 second after being thrown. For problem B, we will be able to answer this question if we can find the y-coordinate of the ball at the time it hits the wall, namely at t, which is equal to 1 and 1500 second. We need the y equation of motion. The initial y velocity of the ball is the initial velocity in y, which is equal to v sub 0 sine theta sub 0, which is equal to 25 meters per second sine 40 degrees, which yields to 16 and 700 meter per second. And the y acceleration of the ball is a sub y, which is equal to negative g, giving us y, which is equal to initial velocity in y times t plus 1 half a sub y t squared, which is now equal to 16 and 700 meter per second times t minus 1 half gt squared. For problem C, the x and y components of the ball's velocity at the time of impact, namely at t, which is equal to 1 and 1500 second, are found from second kinematic equation, which is a is equal to v minus v sub 0 over t. Manipulating this equation, we obtained v sub x is equal to v sub 0 in x plus a sub x times t is equal to 19 and 2/10 meter per second plus 0 times t, which yields to 19 and 2/10 meters per second. And v sub y is equal to v sub 0 in y plus a sub yt, which is equal to 16 and 700 meter per second plus negative 9 and 8/10 meter per second squared times 1 and 1500 second, which yields to positive 4 and 8/10 meter per second.
two-dimensional motion worth studying about is circular motion. A car rounding a rotunda, the recreational rides such as Ferris wheels and carousels, satellites orbiting Earth, and a yo-yo whirling on a string are examples of circular motion.
Uniform circular motion is the motion of an object traveling at a constant speed on a circular path. If the speed varies, then it is called non-uniform circular motion. The number of cycles or revolutions of a body has completed per unit of time is called frequency. In symbol, we have lowercase letter f.
On the other hand, the time for an object to have one complete revolution is called period, or in uppercase letter t. Notice that assumed in definition is the circular path with a given radius r that defines the trajectory of the motion. Also notice that the velocity v at any time is along the tangent of circular path at where the object is.
The circumference of a circle over the amount of time the object traveled in either in terms of frequency or period is referred to as tangential speed. The velocity, represented by lowercase v of a body moving in a circular path with radius of curvature, represented by lowercase r, at any instant is directed tangentially. Hence, it is called tangential velocity. The direction of tangential velocity is always changing, but its magnitude may or may not be constant.
In uniform circular motion, there is no tangential component of acceleration. The acceleration of the particle is directed toward the center of the circle and has magnitude a sub r, which is equal to v squared over r, where r is the radius of the circular path and v is the constant speed of the particle. Because of the direction of the acceleration, which is toward the center, we say that a particle in uniform circular motion has centripetal acceleration. For our first example, a child sits at a distance of 3 meters from the axis of merry-go-round in an amusement park. If merry-go-round makes 2 revolutions in 5 seconds, find the tangential speed and the centripetal acceleration of the child. First, we let the radius of curvature be r, which is equal to 3 meters. The distance that the child travels if the merry-go-round makes 2 revolutions in 2 times the circumference of her circular path. Recall that circumference is equal to 2 pi r. Thus, the total distance traveled is equal to 2 times 2 pi r, which is equal to 2 times 2 pi times 3 meters, which yields to 37 and 6800 meter. We now have v, which is equal to the total distance traveled over time. We now have 37 and 6800 meter over 5 seconds, which yields to 7 and 5400 meter per second. Using the equation for centripetal acceleration, we obtained a sub r is equal to v squared over r. Substituting the obtained values, we have 7 and 5400 meter per second squared over 3 meters is equal to 18 and 7500 meter per second squared. For our next example, in one model of the hydrogen atom, an electron orbits a proton in a circle of radius 5 and 2800 times 10 to the negative 11 meters with a speed of 2 and 1800 times 10 raised to 6 meters per second. What is the acceleration of the electron in this model? What is the period of the motion? For question A, the electron moves in a circle with constant speed. It is accelerating toward the center of the circle, and the acceleration has magnitude a sub r is equal to v squared over r. Substituting the given values, we have a sub r, which is equal to v squared over r, is equal to 2 and 1800 times 10 raised to 6 meters per second squared, all over 5 and 2800 times 10 raised to negative 11 meters, which yields to 9 times 10 raised to 22 meters per second squared. For problem B, as the electron makes one trip around the circle of radius r, it moves a distance 2 pi r, or the circumference of the circle. If t is the period of the motion, then the speed of the electron is given by the ratio of distance to time. We have v is equal to 2 pi r over t. Manipulating the formula to obtain the period t, we have t, which is equal to 2 pi r over v. And substituting the given values, we get t, which is equal to 2 pi times 5 and 2800 times 10 raised to negative 11 meters, all over 2 and 1800 times 10 raised to 6 meters per second, which yields to 1 and 5200 times 10 raised to negative 16 seconds. The period of the electron's motion is 1 and 5200 times 10 raised to negative 16 seconds. On your Google Classroom, kindly open the folder with the name Check Your Understanding. There will be 2 sets of exercises that could help you analyze and assess what you have learned from this topic. We have the multiple choice and problem solving.
Thank you very much for watching.
We hope that you learned.
See you on our next topic. Bye!